Statics Made Easy, brought to you by STEM Buds, the online multimedia question and answer forum for STEM students. Here was the question asked. Basically, this person wants a general way to solve truss problems and they want to learn about zero force members. So I will talk about the method of joints and how to recognize zero force members. Let's first delve into some general steps to take to solve these types of problems, and then we will look at an example that I will solve for you. Step 1 is the structure statically determinate. In a basic statics course, most of the structures will be. This ultimately allows us to set our equilibrium equations to 0. Step 2, apply the moments equations. Step 3, isolate the joints. Draw the free body diagrams, aka FBDs, and apply equilibrium equations. Step 4, repeat step 3 until structure is resolved. And now on to the example. In this problem, we are asked to find all internal forces within the structure. First, take note of joint E and joint F. Joint E is what is known as a pin and will have two reaction forces, and joint F is known as a roller and will only have one reaction force. The roller's reaction force will be in the y direction because it is free to move in the x directions. We have unknown reaction forces at joints E and F, so we will use moments to resolve them. This step does not include any of the internal forces of the beams. When we look at this structure, it makes sense to take the moment about E because that only leaves one unknown force, F sub y, which will allow us to solve the equation. I chose counterclockwise to be positive for the moment convention. To determine if a given force is positive or negative in your moment equation, ask yourself this question. If the joint I am taking the moment about were fixed, joint E, and the rest of the structure was free to rotate, which direction would the structure rotate when only considering the force I am examining? So the structure is fixed at E, and the reaction force at F would rotate it counterclockwise, so it is positive in our equation. The two 900 Newton forces would rotate the structure clockwise, so they are negative in our equation. We solve for F sub y in our moment equation, and now we can apply our equilibrium equations in the y and x directions to solve for the reactions at E. Now notice I chose a convention here. Up is positive for y and right is positive. Up is the positive direction for y and right is the positive direction for x. It is important to choose a convention and keep it for the remainder of the problem. Now let's isolate our first joint. When isolating joints, always start with one where there is at least one known force and only two unknown forces. Keeping this in mind, we will isolate joint E and draw the FBD. Before we look at the isolated joint, pause this video and draw the entire truss diagram as it is seen here so that you can reference it quickly during the video. Examine our FBD. The internal forces, represented by the blue arrows, are pointing away from the joint. Always draw them like this, pointing away from the joint. We apply our first equilibrium equation in the y direction. We have FEC pointing up, so it is positive in the equation, and E sub y is also pointing up, so it is positive as well. So we write this equation with the variables, and then we plug in the values. We already solved for E sub y previously, and it was negative, so simply plug this value in. Notice that our E sub y arrow pointed up in the FBD, so we are adding it in the equation, but the actual value of E sub y is negative, so you actually end up subtracting E sub y. This is why it is important to write out the equations with variables and then plug in your values and solve. We are going to see the same thing in the x direction. In the FBD, E sub x is pointing to the right, so when we initially are writing the equation, we add it. However, when we plug in the value, it turns that term negative. Now let's choose the second joint. We look at the diagram and see that joint F has two forces known, F sub y and FFE, and two unknown, so let's isolate it next. Let's sum the forces in the x first. We draw the internal forces pointing away and write out the equation in variables. FFC's x component is pointing to the left, so we subtract it. FFE is pointing to the left, so we subtract it in the equation as well. We also need to make sure that we are only adding FFC's x component, so we want to take the cosine here, which is 3 over 3.75 meters. Now we plug in our known values and solve. Now to the y direction. Write out the equation first according to your FBD. Now focus on FFC here. Seem familiar? We are adding it in the original equation because of our y convention, but we end up subtracting it because of its actual value. You can use the previous 3 slides to effectively resolve all the internal forces. I won't describe the next slides at all because it is the same exact process. I will show you them for a couple seconds so that you can pause the video and look at the equations done out. Solve the rest of the problem yourself and use my answer to check yours. The next joint you can solve is joint C. Then we can solve joint A, And finally, we can solve joint D. Now you will notice that two of the internal forces, FBA and FBD, were equal to 0. They are zero force members, and if we knew the rules of zero force members, we would have been able to point these guys out from the beginning without writing any of the equations. Write these rules down on note cards and memorize them. It is important to note that these only apply to joints that are not subjected to external forces and are not supported by a pin or roller, i.e. in this problem, joints A, C, E, and F are ruled out. So which rule applied to this problem? Well, take a look at Rule 1. We have a joint that connects two members where the angle between them is different than 180 degrees, thus making both members zero force members. And here is a representation of Rule 3 because it is kind of tough to picture. You are now ready to use the method of joints on trusses like this one. Thank you.